This is the TransLab, the laboratory for research and development of computational models applied to air transportation in the Department of Computer Science, University of Brasilia. And on this video, we're going to present a video abstract for a research paper called 4D Trajectory for Fluke Detection and Resolution using Decision Tree Pruning Method. The researchers that contributed to this work are Lucas Monteiro, Victor Ribeiro, Cristiano Garcia, Geraldo Rocha Filho, and Li Weideng. On this introduction, we're going to talk about some of the key concepts required to understand this research. The first of them are the trajectory-based operations, or TBO. This is a new technology that enables strategic long-term conflict resolution trajectories that combine security and efficiency. The next concept is the four-dimensional navigation, or 4D navigation, where the time is added as a fourth dimension to the three dimensions of space. So now we have a flight being represented as a series of four-dimensional points in space-time. And the third concept is conflict detection and resolution, or CDR. Now that we have TBO and 4D navigation, we need to determine if there is not enough separation for any of these aircraft, and if a conflict is found, we need to find an efficient way to solve it. So, the main contribution of this work is a new framework of CDR for 4D navigation management using not only SQL database for conflict detection and decision tree pruning method for conflict resolution. Now, the proposed solution for conflict resolution uses a tree data structure which contains combinations of all trajectories for all aircraft. On this tree, each level corresponds to an aircraft, and each node of a level corresponds to a trajectory of that aircraft. This modeling makes it possible to identify an optimal combination of trajectories without conflicts, as we're going to see on the next slide. Now we're going to explain the tree pruning approach. It is inspired by the classic alpha-beta algorithm. So on the top left side of the screen, we have two flights, flight ABC on the first line and flight XYZ on the second line. Suppose that trajectory A is the best trajectory for flight ABC, and that trajectory B is the best trajectory for flight XYZ. The tree on the bottom shows what happens when we prune this tree, eliminating all the other nodes that cannot be reached. You can see that the whole subtree to the right has been eliminated because once trajectory B for the flight ABC has been eliminated, all the nodes and leaves below it are also discarded. As we can see, this tree pruning approach increases significantly the ability to analyze larger trees considering the same computational resources. Now we're going to see a case study where a simulation scenario has been used for conflict detection. This scenario is composed by a selection of 9 airports in Brazil. Those airports are responsible for 58% of the national air traffic in 2018. The flight plans for those airports are used as input for the trajectory predictor, and the generated trajectories are stored on the NoSQL database for conflict detection. For the conflict resolution simulation, scenarios with randomly generated data were used to evaluate the proposal for conflict resolution. Synthetic data allowed for greater control and complexity of the task when compared with real-world data. The tests were conducted considering the standard trajectory and as many as 50 alternative trajectories. For each combination of number of aircraft and number of trajectories per aircraft, successive tests were performed 30 times in order to ensure that the results obtained are statistically sustainable. And now we can see the results for the conflict detection test. From the table, we can see that when 32 threads were used for detecting conflicts in more than 830,000 waypoints, both databases have successfully detected more than 8,000 conflicts in less than 18 seconds. This shows the performance of conflict detection using the combination of all possible trajectories to be performed by the aircraft, with different combinations of flight plan executions. And these are the results for the conflict resolution. During the test, if the execution of a number of flights and trajectories increases above a certain limit, those numbers are not considered. From the graphic, we can see that the pruning approach delivers results that are acceptable for all combinations of trajectories per flight and flights in a conflict cluster. And now we get to the conclusions. The main contribution of this research is the development of a new computational solution for CDR and 4D trajectories that incorporates a trajectory predictor, decision tree pruning method, and databases specifically designed for big data. The developed application consumes information from several sources conveniently aggregated in NoSQL, Cassandra, and MongoDB databases. The proposed storage architecture is designed to comply with the Swing paradigm, as this architecture can manage and provide information to support the decision-making process of air traffic stakeholders.